back. That's right. So as the Grignard approaches, it's going to push the oxygen back. So the oxygen will end up going back, and the Grignard will end up in front. Common mistake here is if people drew this. I used to do this all the time. I used to add a carbon. So to prevent doing that, I will count carbons. 1, 2, 3. There are only 3 carbons in that nucleophile. So there should only be 3 carbons added to the product. All right? That is incorrect. What's the other option? It's the Grignard attacking from the back. If the Grignard attacks from the back, what's going to happen to the alcohol? It's going to be pushed up. Right. So again, we will keep the carbon-carbon bond in the plane forward. The alcohol gets pushed up because the Grignard attacked from the back. Questions so far? Okay. Well, what is the stereochemical relationship between these two products? Well, we could draw them out and try to rotate them and flip them and see if there's a mirror plane, or we can notice that it only has one stereocenter. If you only have one stereocenter, what is the only possibility for stereoisomers? Enantiomers. Go look at the flow chart. So these guys are enantiomers. Whoops, I ran out of room. Enantiomers of each other. Any questions on that? That makes things a lot easier. One chiral center, definitely going to be enantiomers. And if they're enantiomers, there are only 2 possible stereoisomers. One of them is going to be an R, one of them is going to be an S. And what do you think the ratio of the R and S is going to be? 50-50. The nucleophile has no preference to come from the top or the bottom. It's a completely flat molecule. So we can draw both of these products out, or if you want to save some time, you can draw one, and then underneath it write racemic. That tells me that you know there are 2 enantiomer products produced. Here's one of them. Racemic means the other one's there as well, 50-50. Saves a lot of time on tests instead of drawing them both out. Any questions on that? Excellent. All right, moving along then. So now we're going to talk about another named reagent. We just looked at Grignard reagents and how they react with carbonyls. Now we're going to talk about the Gilman reagents. So these are very similar to Grignard reagents. We're going to be making nucleophilic carbon fragments. But instead of magnesium, which is used in Grignard, we're going to use lithium and copper to achieve the same type of reactivity. And making Gilman reagents is a 2-step process. The first is, you start with an alkyl halide and you convert it into an alkyl lithium. So if you take an alkyl halide and you treat it with 2 equivalents of lithium metal, then the lithium will actually displace the bromine. So you end up with this, which is an alkyl lithium. Alkyl lithiums are insanely reactive. They are far too reactive to use in some chemical reactions. So we have to kind of temper down the reactivity. So these are excellent bases and nucleophiles. They're so good, they're kind of hard to control. They're kind of hard to work with, actually. They spontaneously flame when they come into contact with the air. That's how reactive they are. So the second step of making a Gilman reagent is by by converting it into a more stable cuprate. So it's called a lithium diorganocuprate. You add copper iodide or copper chloride or copper bromide, essentially a copper salt, and the copper is going to act like the magnesium did, and it's going to insert itself in between the carbon lithium bonds. And in terms of stoichiometry, because of the number of substituents that a carbon can hold on it, we actually get two alkyl groups. So these structures look like this. You have copper and lithium. And two alkyl groups. Okay? So that's what we're representing with this brackets around the alkyl group and the number 2. So we have tamed these reagents. And if you look at the polarization of the copper-carbon bond, copper has an electronegativity of 1.9 and carbon 2.5. So are the electrons in that bond trending towards the copper or towards the carbons? Towards the carbons, that's right. So you can draw polarization arrows showing the electrons moving towards the carbon, making the electrons, or making the carbons electronegative, and thus nucleophilic. So, to summarize, we have Grignard reagents, which makes an organomagnesium compound, and that gives a nucleophilic carbon. And we have Gilman reagents, which make an organocuprate compound, still nucleophilic at the carbon. Kind of the same thing. So why would you make a Gilman versus a Grignard reagent if you're accomplishing the same type of nucleophilicity of carbon? It's because Gilman reagents are particularly good at reacting with alkyl halides. Grignard reagents, we saw previously, reacting with carbonyl groups. So, when you want to form a bond with an alkyl halide, you use Gilman reagent. And again, we're going to look at the two materials and determine that's a nucleophilic carbon, that's an electrophilic carbon, because of the polarization of those bonds. So there's going to be an attack from the nucleophilic carbon onto the electrophilic carbon, kicking off the iodine, and the product of the reaction is this. There you go. So we have formed a carbon-carbon bond, much like the Grignard reagent. The difference here is that we're forming a bond with an alkyl halide as opposed to ketone or an alkyne. And I chose the colors of the bonds very carefully because, again, people tend to screw up here when it comes to adding or subtracting carbon. The new bond is the one shown in baby blue. So if we count out 1, 2, 3, 4 bonds on the black piece, then we know we have the correct number of carbons. And then if you switch to the red, you can count 1, 2, 3, 4. Oh, sure. See what happens? Happens to everyone. So I still, to this day, number the carbon chains to make sure I don't add too many. Any questions about that? Yes?
We know that two alkyl groups are attached to copper, and the forces are acting in opposite directions, and they are the same forces. Wouldn't these forces cancel out each other?
In terms of the overall polarity of the molecule, yeah, they might cancel out, depending on the direction of those two alkyl groups on the copper, right? So they could be in this direction and they don't cancel out. But we're not looking at the overall polarity of the molecule, we're looking at the overall polarity of that bond to describe the reactivity at that atom. Okay? Great question. Yes?
Do we have to balance the equation?
We do not have to balance the equations. So some people will say, but there is 2 of these long butyl chains for every one of these. So in reality, you only need to use 0.5 equivalents of copper experimentally to 1 equivalent of this, because there are 2 nucleophilic chains of copper. We're not going to worry about that. These questions are going to be phrased mostly as just predict the product. You don't have to worry about balancing the equation or side reactions or anything like that. Oh, great question. What happened to the iodine and the copper and the lithium? Those just form copper iodide